We're now looking at, we're looking at an elastic, sorry to say anelastic, not inelastic problem. Need you to do this here so we can get more practice. Now, in a traditional problem, you would, like what we're going to be working on tomorrow, it's going to be a word-based problem where you're going to have to sort of analyze it, draw a picture. Drawing a picture is going to be really important because if you don't know which way the objects are moving, certainly you're not going to plug it into the equation correctly. So I'm going to kind of model a little bit here of what you would do if you had a problem. So in this scenario, I'm trying to help you. We have a cart, which we're calling mass 1, and M1 equals 30 kilograms. So we say, hey, you have a bumper car, it's 30 kilograms, and it's moving initially with a velocity of 4 meters per second to the right. Okay. Now, it's helpful to write those variables below the cart because if you look at it, we're trying to keep everything in order. Okay. You know what the mass is, you know what the velocity is, so you can plug it in. It then is being approached by a larger mass 2, that is moving in the opposite direction. So mass 2 is 45 kilograms. And it's moving in the opposite direction at 2 meters per second. How would I write that? It's moving in the opposite direction, yes, negative 2 meters per second. Because if you had not recognized that, there's a big difference between a car coming and being hit this way versus going together. Now, I typically, you can put a dotted line. Sometimes I'll put a slash. The slash basically separates the difference between what happened before and what happened after. If you actually look, we're not actually looking at the collision itself. We're looking at what's the scenario before the collision and what's the scenario after. If you want to know how much force and time it takes to do that, that's where the impulse momentum equation is. We're told afterward some information about the mass 1 cart. Still has the same mass, but we're told afterward, or at least we observe afterward, that it is not moving 4, it is moving a little bit slower. Sorry, not V2. V1F is 2.5 meters per second. So it's still moving in the same direction, it just slowed down a little bit. And we are wanting to know what is the velocity, not only the speed, but what is the velocity direction of this second car. It's not always obvious. It really is not always obvious. Sometimes you can say, hey, I have a prediction it's going to be this, or it's going to be going to the right, or left, or 0, or it's going to be more than this, or less than this. And this is a scenario where it may not be as obvious as what's going on here. This is what I mean by model and say, draw your diagram, write the variables underneath. It's literally in the directions you'll get in the worksheet tomorrow. Write the variables and their values under the correct part of each diagram. Write the equation blank. I am going to ask you to write the equation blank anytime we can get practice writing it. Equals, because it is conservation. And figuring out what do we have and what do we not have. We know M1, we know M2. We know the initial velocity of the carts. We know the final velocity of the first cart, but we do not know the final velocity of the second cart. We're finding stuff that's after. You realize there's 6 variables here, okay? M1, M2, V1I, V2I, V1F, V2F. The problem can be a scenario where you're finding any one of these. So you could have really a lot of different possibilities. So making sure we plug in the values and making sure we pay attention to direction. So 30 times 4. (45) times negative 2. Done the hard work. Show that the initial velocity of the second cart is negative 2. If we had not plugged that in right, everything would have gone sideways. So we still may not have a prediction. 30 times 4 is 120. 45 times negative 2 is negative 90. 30 times 2.5, is it 75? If we actually look here at the beginning, or at this point I am right now, the left side, the total momentum before is 120 plus negative 90, which is 30. 30, that is the total. We already have 75 on the right side, which means what does the momentum have to be for the second mass? If we have a total of 30 over here, positive 30, and we already have positive 75, this has to be what type of number? It has to be a negative momentum. You can't add a positive number to 75 to get 30. So our prediction based on this is that, well, based on that, V2F should probably be a negative number. And that's what we get. We get 30 equals 75 plus 45. And by subtracting 75, we do end up getting a negative number on the left side, which is going to give us a negative velocity. So it's not necessarily a point for you to say, hey, does that make sense? It makes sense in the fact that it made the two sides equal to each other. It wasn't necessarily something that you could have easily predicted going into this, knowing that it would be going to the left or going to the right. But at least you can say, hey, does one at least maybe fall into the ballpark of being realistic? Sure. If we had something that was 10, 20, 30, 100,000, something like that, then you'd be like, something doesn't quite work here. Now, since I actually did this with a calculator, an online calculator, if we did plug in 30, 4, 45, all those numbers here into this, within really close rounding, we'd see that the total kinetic energy before and the total kinetic energy after would be the same. We're going to go ahead and hold off on doing that right now. So -1. Let's look at an inelastic, sorry, not inelastic, but let's look at an explosion / recoil separation type problem. One we've actually talked about in the past, or at least referred to. So here's our space station with our door. It has a doorknob, because that's how space stations work. Doorknobs are just enough to lock the door, prevent all of the explosions coming out. That's our space station. Before we do this, I want to actually refer to something in a worksheet here. Hold on. Let me